Bridget is having a great day. Congratulations, Bridget. Well earned. Yeah, I bet that was a little bit stressful.
Why are you here, though?
Yeah. Thank you for coming. I bet.
Yeah.
Boy, yes, why are you here? But no, congratulations. That's awesome. Anybody else have good news? And we have bad news. We can plot that too. Anybody want to grouse and have like community support? I hate my job. Oh, I hear you. No, sorry. Anyway, no, I don't. What's that?
Papers are the worst.
Papers are pretty bad. I agree. Finals, terrible.
I would rather have finals, actually.
Final paper.
No.
Supervisors. Yeah. Well, I got a couple notes for you on all that. Yeah, papers are the worst. And your homework papers aren't graded still, so sorry. One of you came to my office and said, boy, you're really not on the ball these days. And and for that reason, I'm just never going to... No, I'm just kidding. I will have them graded. That's not what I think. That's what I heard from it.
Wow. I'm pretty sure we were all thinking it.
No, I'm messing around. No, actually, the reality of it is I'm not on the ball these days. And I have escaped. I'm not a good picture of balance in my life because that other half of my job is killing me. And so once I go back and kill it, things will get better. And that's my excuse. My apologies. I'll have your homework graded to you in the next couple of days. But in terms of revisions, they all won't be due until the end of the semester. Like the day the revisions of the projects are due. So there won't be any pressure to have to hurry up and get things done. All right. That's homework. I'm supposed to announce to you that next week in this class, I will be handing out student evaluations. So you can legitimately talk about me not being on the ball without me knowing who you are. I will tell you that if you're interested, I will. No. I was going to say something about bribing you or anything else, and maybe we'll have pizza next week. But no, I'm not opposed to like making you full before you give a student evaluation. Ice cream could be done. You know, we're all on the note here. We can figure this out. But in all actuality, I guess we're supposed to announce in campus policy. I'm supposed to announce to you a week ahead of time. So I have the forms. I will bring them for you. I'll ask one of you to take them up to the office for us. I actually do I take them seriously, although the thing about our forms, we don't have a good, nice, structured back end of it to you can answer questions about the class. It's like a blank form that you write on the back and maybe someone looks at. So I might think of a few questions to write, or my own form to give you as well, because I'd like better feedback. I just don't want the score that you're going to give me. I want to know how you feel. So I'm more of a qualitative person these days. Frustrated, tired, salty. Yeah, well, that sums up my life too. So, well, now that we all feel the same. But no, that'll be coming next week. So just a heads up on that. I do take those seriously. I'd like to know how you feel, and want to give you the anonymity it may take to do so. Okay, so we left off last week with me dropping bombs on classical test theory. That's right. I'll bet the next day's class of classical test theory was amazing after that. No, not really. Oh, it was different. I'm going to pick up where we left off last time and talk about the classical test theory connection a little bit because it's kind of important to me. It underscores a bigger picture that I really want to get across to all of you, which is whatever you're doing to data, there's something you're implying statistically. There's a bigger picture than that, which is that model that you're doing statistically probably is a very limited model if you're doing it without a model for itself. So in the bigger, broader picture of statistics, model-based statistics everywhere, you'll have a contingent of people out there who'll say, well, we don't want a model, it's too fancy, it takes too much time and effort, whatever, but you're already doing a model is what I'd say back. And that's what the classical test theory connection does to me. But after that, what we're going to do is then so then I'm trying to solidify what a score is and how it works for you. Then the next thing is how on earth would you use it if you could use it better in an analysis? And that's where we're going to get into talking about multiple imputation. We're going to treat the score as a missing piece of data. We're going to talk a little about Bayesian statistics. And I'm going to go again about what's in the score itself. So one thing that I won't say is I'm going to try to teach you the way that I think is the best. But clearly everybody does it adding stuff up, putting it in the model, or just taking a test score and putting it in the model. So I'd like to delineate the sources of error when that happens. So the other flip to this is if you're going to do it, list out where things could be going wrong. Because at that point, you can essentially have a conversation about how realistic it is your analysis is telling you the right thing, or better yet, how much of it is not, it's just voodoo. Cool? Questions about last week before we begin? All right. So, big picture, big purpose is that simultaneous models are the best. If you don't do your simultaneous model, you end up having places where error can propagate. This is a problem. Propagate, what a great word. Right? I don't know. Makes me think of, when I hear propagate, it makes me think of like learning in mathematics, like learning computer science a little bit. That too. No problem. Can we get a soundboard? Can somebody like make commentary behind my conversation? Some cheers when I do something well, or boos or something. That'd be awesome. When I taught Psych 790 and 791 when I was here the last time, I encouraged my students to do random stuff like that, and they actually took me up on it. I think it's kind of fun. One of the things I got them to do was to bring in those. What's the word game where you have the buzzer? Taboo. That's our, the catchphrase also. They brought in their taboo buzzers, and evidently everybody has a game of taboo. And so when I said something that wasn't quite making sense, someone would just buzz in. That was awesome. So soundboard would be good. So if you make commentary, that's good. Anyway, I'd like to create a way to show you how to get back to where the results are as close to the simultaneous analysis as possible. And it's just trying to understand where the error is coming from and what we can do about it. And even with what I'm going to show you today, there's still sources of error in it. And actually, probably some of the worst sources of error are still in there. And we're going to talk about that. So, Jennifer's thought? Sarcasm. Or go ahead, be cynic.
I mean, you should become a motivational speaker.
Yeah.
That was so
I just want to show you how to be less shitty. That's just it. Just a little bit, all right? I'm sorry. Is that the motivational speaker? Try not to suck so much.
I'm motivated.
All right, I had this before, the test scores. Remember, this is the context I'm working in. I use just a total score or some scores all the time, or, you don't want to use factor scores. They're terrible until you want to look at GRE scores, and they're totally okay. I can go a step further than that. I can say, not only are your scores important, we're going to tell whether or not your teacher's doing a good job by seeing if your scores are growing. I had that from Julie's comment last week of the students and where they needed to be and so forth. Yeah, that's the world we're in, huh? All right. So, picking up from last time, we have these 3 test items, GRI1, GRI3, and GRI5. They're all ranging in, they're all numbers that go from 1 to 6. That means you could have a total score that goes from 3 to 18. Does anyone really believe these are continuous data? No. That's a big-time source of error. Yeah, there we go. There's our sum score. That means that over half our sample, or over half of our sample had the lowest. 1, 1, 1. Doesn't that look like a continuum to us? No. That looks like a chi-square at top. A little bit. Anyway, so do you remember when we? Do you remember that the fun part of last week when we used multivariate normal distributions? We're like, what's a factor score again? Oh, a factor score. That was we figured out a factor score. If we're doing a CFA model, the factor score is the mean of a distribution. Actually, we can figure out what the distribution is. It's multivariate normal. Each score has its distribution. The mean of it is this complicated matrix product of all the parameters we have, and the variance of it and covariance of all the scores is also part of the same thing. Today, I'm actually going to use that to our benefit. So one of the things I was about to do this week was switch over to M+ because I needed help to try to get something into effect. And I was going to try to show you something to do with Bayesian and multiple imputation. And then I realized M plus really stinks at Bayesian stuff. They're doing things that aren't well documented. Not only that, but they're also kind of circumventing what we're doing here. So I was like, okay, great, now what? Which is really where we're at the end of this. Next time I teach this class, we're going to use my software that is still in development that would be much more copacetic of doing all this, putting all together. Anyway, I had to use this. Point being, I had to use this result. I got there I was doing this on Sunday. I was like, Sunday afternoon, it's beautiful outside. I need a stinking standard error of a factor score. Right? Do you ever feel, if you ever found yourself in that position where you're like, I'm just, I was going to mow the lawn, but I was out of gas, so I need to go get some gas. I was like, I'm going to make a lecture, and I didn't have a standard error. So I had to go and make my standard error. So it's freshly baked, though. Anyway, all that math means for us today is that your factor scores are multivariate normal, and we're going to use that over and over and over again. It makes life a lot easier. In reality, what we're going to see is the factor score itself, if your model isn't a CFA. So if you don't believe your data are truly continuous, it's not guaranteed that you have a multivariate normal there. So what I'm going to tell you today doesn't apply. It takes a different form. The bigger picture of it still applies, but the form of it might be a little bit more specific. Got it? All right. Have you ever wondered where a standard error comes from? My daughter asked me that. Dad, where do standard errors come from? And I said, well, Daphne, when matrices... No, sorry. Never mind. What's that? Nothing. All right. So first thing I wanted to do was connect the sum score to the factor score. I tried to do that in a way where I said, hey, look, if we take our sum score is correlated with has a correlation of 1 with factor scores from a CFA model where we have parallel items. Parallel items, once again, of course, you would have thought I would have fixed the dang typos. Parallel items have the same factor loading for each item and the same unique variance for each item. So what we're estimating when we do this analysis is 3 item means, 1 factor loading, and 1 unique variance itself. So this is remind you of the fun we had toward the end of last class after the matrix. And this was the cool thing to me. I did this and was like, whoa, look at that. Yeah. When I see a line that looks like that, I'm like, something's going on here, right? And this is where I broke down and I told you, I've been told the whole time that sum scores are tau equivalent, not parallel, right? Tau equivalent being the next model. But here's our parallel items. What we can see is the difference between any two. So this is our model fit. Let me go through this. Our model itself, our loadings are constrained to be equal right here, and our unique variances are all equal. The factor scores come from the predict function in Lavon, or in R. So once you get this model fit to work, once you put it through the SEM function, if you take that thing and shove it into something called predict, you get out of it factor scores. So that sounds good. This plot right here takes the factor scores on the y-axis and puts it against the sum score on the x-axis right there. And you'll note they're perfectly aligned, right? This is a scatter plot, but I drew a line through the middle of it because I could, right? It's a perfect correlation. The only thing that differs is the scale, right? What's on the x-axis is not quite what's on the y-axis, but we could tinker with it to make it work. So I found that pretty cool, right? I didn't even realize. I'm making a new lecture and I'm like, whoa, the things I should know, right? Huh. Anyway. So looking at it a little bit more closely, here's a sum score of 3 at the top. That sum score of 3 has a factor score of negative 0.715. Right, so that's the lowest score that you have there. 3, negative 0.715. This next bit of sum scores are sum scores of 4. And you'll see each of them, of course, have the same factor score. And that the factor score, for every 1 unit of the sum score that goes up, the factor score goes up by 0.364. So if you think about it, difference of 1 point on the sum score scale is 0.361 factor. Is there anything we could do on the factor scale to change that unit thing? If we change the factor variance, that would change. All right, we standardized the factor. We said this factor has a variance of 1. With the variance of 1, it kind of squishes things in. It takes it from our 1 unit apart and pushes it down to 0.36 units. Right, so if we change the factor variance, I didn't here, but if we change it from 1 to, well, heck, we could even change the mean of the factor to be the mean of the sum score distribution, the variance of the sum score distribution. I imagine we'd have very close to the sum score 1 unit apart with it, which is kind of cool too, right? So now all of a sudden we're getting sum scores back from factor scores? What? An RMSEA on a sum score? Crazy. Anyway, what we really want to do is the idea of, like, this is a kind of a squishing of the factor scores itself. It's the opposite of pandiculation, right? Which is kind of a full body stretch between these 1 units, all right? So you know that word? What's that?
Sorry, I'm playing with you.
Uh-oh. That's okay. If it's my voice, I heard echo. I'm like, I'm sorry.
She's lowering your voice.
That's okay. I think that's pretty awesome. If you're gonna like play something, play my voice. Actually, I really hate the sound of my own voice. So that the fact that I tape my lectures, it drives me nuts if I ever accidentally click on it because I don't want to hear me. I don't know how you put up with this. Yeah, that's good. At least I hope there's something there. I don't know how you put up with this. That's all I gotta say. Anyway, so I find this a little bit interesting. The next step that I wanted to show you was what happens when we go up to a factor score of 5. That value is just another, if you add 0.36 to it, we get up to 0.01, which is the factor score for it. So we were cool with all that before. Brings back fun memories of last time. Love it. Awesome. So did the model fit? We said the model sort of fit. It's kind of interesting to me. So like the robust ML tells you it fits, but the regular ML tells a very different story over here. It's not really fitting. So one way or the other, we could. Now, we talked a little bit about reliability, and this is where I told you before, I don't really like to dwell on reliabilities too much because there should just be one. Right? Reliability should be the proportion of variance in a score that's due to the trait you're measuring. Right? And so we've got alpha and we've got omega and whatever else. And I'm just saying if you stick with the idea of how this works out, we need something that talks about trait variance, and we need something that talks about variance due to error. Right? This is this standard error of the factor score squared. It's the variance of the factor score is your variance of error. It's your measurement error in this factor score context. The variance of the factor itself is kind of like your variance of true score. The factor is like the true score, which really sounds terrible, right? True gambling score. All right. So when we put all this in, we saw the factor score reliability was 0.73. And I asked what was the reliability of the sum score. By the way, how I found that? I took the variance of the factor. I set this thing equal to 1 based on the analysis. I just standardized with the standardized factor. So this thing was 1. And in Levon, I had to compute what the standard error of the factor score was, which was right here. So the actual variance of it was this thing squared, 0.608 squared itself. So if I go back a slide, this thing is 0.608 squared. Right? So putting it all together, I get a reliability of 0.729. I hear 0.8 is nirvana for reliability, right? Actually, there's some variance in that. Anybody have people say they want more or less reliability in their field? No? Anybody heard what reliability standard in their field is? Is anybody afraid of a high reliability? Let me ask you that. That's a question I never heard before I came here to work the last time.
Well, I would be curious about an exceptionally high reliability.
What's up with that, right? I've heard the argument, this was a surprising thing to me, that you don't want too high a reliability because then you'll shrink your chance at validity, right? You're honing in on the target so much that if the target's wrong, then you're off. But I don't know that that's really what I'm worried about. I think reliability is Like having a high reliability is the most awesome thing there is. It's like thinking about. I remember having this discussion in Fraser the last time I was here. Like if you're going to go move and take one of these desks with you out the door, you want to make sure it fits the door, right? So do you grab the ruler that has 0.7 reliability, right, and not be able to fit it through because the ruler was wrong and had a little error to it, or do you want the most precise thing there is? And so validity, I always feel like is overblown. I mean, I'm kind of a cynic when it comes to validity, but I do think so long as nothing's suspicious with the analysis or whatever else, I think high reliability is the higher the better. Everything gets better with high reliability. And all this stuff I have to talk, if you had a reliability of 1, all this stuff we have to talk about today, you could still do, but it wouldn't matter because you have you have a perfectly measured variable itself. So, anyway. So part of the fun last time was to take classical test theory, which was your total score is equal to something about true score and something about error for each person. Compare it with factor analysis, right? So here's a 1-factor model. Bless you. So if we take our total score, it's the sum of all the items. We then go and put in the place of the items the factor model, what the factor model says for it. And we can combine like terms, move things through the sum, and so forth. We end up with this part, right? The total score based on the factor model should come from the sum of all the item means, right? That's going to kind of give you your mean of your total score, actually. We should also see that the factor score will be multiplied by a constant that's the sum of all the loadings. And then what's left over is the sum of all the errors. And so if we were to try to map this onto classical test theory a little bit, this part that's error is E, and this part over here is T. That's true score, there's error, right? If we didn't have error, if error was 0, this part right here would be our prediction of what your true score really should be. So when we break all those down, we can then go, since we have a formula for what true score is, we have a formula for what error is, we can go apply algebra. Algebra of expectations is what Rod McDonald would call it. But I can apply some algebra and say, what is the variance of the true score? What is the variance of error? When we work all that through, we see the variance of true score is this constant, the sum of the loadings squared, times whatever our factor variance happens to be. And the variance of error, so long as we have uncorrelated residuals, is the sum of all the error terms. They're all independent if we have uncorrelated residuals. So now, what this formula is doing is saying if it is the case that we're after this total test score and we're summing things up, we can go and take things that we know from a CFA model and use them to put in place into our reliability formula to talk about reliability for that test score. So one of the convenient thing is if you're going to use a test score in what you're doing, you can be doing CFA with it already and get reliability out of it right away. So it's kind of like you're checking your dimensionality and we're getting reliability in the first place. So I kind of like that. I think that's neat. We put those together. Here we end up getting this formula. Our factor variance, this thing was set to 1, so I'm going to put equals 1 here. The sum of the loadings I took from Levon. I could take those and square them. That's what this term right here is. I have 3 loadings that are all equal. So 3 times loading is the sum of them. That thing squared. We have the sum of the unique variances as error. That's 3 times the unique variances because they're all equal. And in Levon, it actually outputs the estimated new parameter, kind of like we'd have this to be in a mediation model, right? Remember in mediation we had to figure out indirect effects between variables. This was the code we would use. This is the same type of syntax for it. We're creating like it's not an indirect effect, it's a combination of parameters. It gives us the reliability. We found that reliability to be 0.629, and you'll see it looks better than the factor score reliability, and that's because the factor scores themselves get smushed in by that normal distribution. Right? The extreme factor scores get brought in on either side, so it looks less variable. That's not cool, The other thing that we found out was that the sum score reliability, this was the Spearman-Brown reliability estimate. And we all remember Spearman and Brown. How could we forget, right? That was where I went on my rant about 1910, and this is modern technology back then. It's an odd perspective to be in. It really is, right? Anyway. So we could look at other factor score models. This was where I went on a tangent. This is sort of a tangent. That whole process, this thing that you see here, the sum of the loading squared being the variance times factor variance is the true score variance. The sum of the unique variances is the error variance. That applies for any CFA model we do. If we want to say that CFA model, now what is that what's that reliability for? It's the reliability for adding up those items. Right? If you add up those items, it's the reliability for it. It's not the reliability for the factor score. It's the reliability for the sum of the items themselves. And that's the hard part to realize. You start talking about reliabilities and different scores, and there are all these things flying around. It's like, I don't know, it's like watching me do garden work, right? Everything's flying up in the air. There's dirt. There's whatever else. I don't do garden work. It's like going to, does anyone have is there a dirt racetrack around here? Sorry. Anyone know what I'm talking about? If you go to sometimes in small towns they'll have dirt tracks where they'll put cars on. They'll just spin and go in circles, and everybody gets dirty. I think that's part of the allure of it. I've never gone myself, but it's like that, just stuff in a haze. I talked about Snoopy's cousin Spike this year. Another character from the Peanuts is Pigpen. Okay. Scores and stuff flying around in Pigpen. You know Pigpen? For those of you who don't, let me. I don't need an image. There he is. He's just dirty. That's like all the scores going around, right? Just everywhere. So, gosh, no. Anyway, back to scores. It's a big hint. The reliability that you do all this complicated formula for is for your score. And I'm going to say don't use the sum score, use the other one, use the factor score itself. So, but actually, when we move on to use the method we talk about a little bit today with the multiple imputation part, reliability is less of a worry because you've already kind of taken measurement error and put it back into the analysis itself. But leave that for another time. So what happens if we loosen the assumption a little bit, if we said, oh, let's take our unique variances and allow those to be different while we still have the same factor loading. These, by the way, are different factor means. If we do that, we end up seeing that we now get a little bit of variation in our factor scores as they compare to the sum scores, right? Here's the factor score on the y, on the x-axis, the sum score on the y, and the point estimate themselves, you'll start to see people start shifting around a little bit. Now again, these are all the scores. If we were to actually take a score and add to it its error band, you'd see the score, the factor score itself would have a wider error. You wouldn't really just be able to distinguish people on either side very easily. You might have to go. Actually, we can find out what we'd have to do. The variance of the factor scores. Do I have it in here? Don't think I estimated it. I did estimate it. Didn't show it to you. But if the last one was 0.6, let's imagine it's close to that. Plus or minus 2 times 0.6 is 1.2. So here is a point on this. 1.2 more than that would be out here. 1.2 less than it would be down here. So any factor score itself would have a distribution that looked like this. Right? So this was supposed to be the mean of that distribution. So if you were to say what person is significantly different, has more gambling tendency than this person, you'd have to look at any factor score where the distribution was not overlapping enough out here. So it'd have to be something like this right here, right? So you could almost draw it in and get a probability out of it if you really wanted to. But too much. So we can do this. We can get our. This is the difference. And what you end up seeing here is that where that shifting in people happens to come from comes from that violation of the assumption of parallel items. When items aren't parallel, that means that some items mean more in the count than others. All right, so summing things together, every item's treated the same. In this model, what we have are 3 different unique variances. We have the same loading, but 3 different unique variances. This is telling us that the bigger the variance, the more the error there is on that item. And sure enough, the more error there is, the less information there is for the factor. Right? So if you were to get 1 point up on the item that has the most error, it would really move you along the factor score just a little bit, or a lot less than if you were to have 1 point higher on the item that has less error. So try to break that down. Take a look at item 1 here. This is a person with a 2 on item 1 versus somebody who didn't answer it with a 1. Sorry. Item 1, the person who answered 1 on all 3, like over half of our people, versus a person who said, oh yeah, I sort of slightly disagree to item 1 versus the others. The factor score difference is negative 0.71 and negative 0.35, or somewhere around 0.36. Right? Now let's compare that with someone who's at item, this person here who doesn't endorse item 1 but endorses item 3. Remember, item 3 has a smaller variance. So the factor score difference, actually, this is the parallel items model. I should be really looking at these two. This difference is 0.30 right about for this first person. I'll put 0.30 here. What about the next one? This next person, by answering a 2 up on item 3, their factor score doesn't jump by 0.3, it actually jumps by 0.45. Right? So if you think about the sum score for each of these people, the sum score is the same. You've got a 4, right? But because the first person got to 4 by going through the item that had a little more error, it didn't get represented as much on the factor score side. Whereas the other side, if you go look at the person who answered more affirmatively to the item with less error, they got a bigger bump in their factor score itself. So what I'm building for you here, you like that? All right. What I'm building for you here is that what we talk about when it comes to sum scores or classical test theory, that items matter. Each item is different. Like the assumption of parallel items says items don't matter. Just any item can be there. But even when you get to tau equivalent items, items matter. Right? You want items that have the least amount of error that could be possible. So I thought that was kind of neat. This is not something I had gone and put down in a lecture before. So you're kind of getting an experimental version of lecture here. But I'm trying to disentangle why the differences lie, because if there weren't any differences before, or better yet, it was a shrinking of the scale, what happens when the items matter? This is what's happening, right? So the variance for this thing was 0.73. If we take the sum score reliability estimate, again using that syntax in Levon, right here at the bottom, although it's a little bit different because we have 3 unique loading variances now. This 0.62 is our reliability for the sum score, right? So 0.73 again, that's reliability for the factor score. 0.62 is reliability should you sum up all the items together. The 0.62, although I will say this, the interesting thing to it, should you sum up all the items together, you actually have another source of error, which is the misordering of people. And so 0.62 is probably not exactly accurate on that either, because you've just switched order a little bit between people. But that 0.62 is what we know as alpha, coefficient alpha. Gutman's alpha, or Cronbach's, Gutman's lambda 6, I can't even talk, Cronbach's alpha. You know, I hear giving lectures where you read your PowerPoint is really bad. But what about lectures where you aren't even reading it and saying the wrong things and they're discredited by it? Is that worse? Is that like here's a sum score for you, right? A classical test theory thing. Is it worse just to read what's on the PowerPoint, or to go and talk about it but be wrong? Oh boy, that's the analogy for what we're doing here. Anyway, so now the reality of it is, though, I taught you CFA this year, and I didn't talk about parallel items. I didn't talk about tau equivalent at all. And so when you're doing CFA, would you ever do those? Probably not. We could check, but if I were to run the unrestricted model, what we thought of as the CFA model from before. All right, here's all 3. I'm estimating all 3 loadings, all 3 unique variances. I have a standardized factor. that model is now the other two, the parallel items, where every loading is equal, every unique variance is equal, is nested within the CFA model, right? Because we could free up the loadings and free up the residual or unique variances and get to CFA. Same thing with tau equivalent. Parallel is actually nested within tau equivalent, and tau equivalent is nested within the full unrestricted CFA. So we have a nice model comparison. I have drilled that into your head. I love the ANOVA function. I was working with M+ this weekend, and I had to run multiple models. I'm like, now I have to go and figure out what the difference is. Like, I have to do the likelihood ratio test. And with MLR, right, you have to go and rescale by a number and everything. Oh, it's just so different. But then again, I hate, pretty much every package has something wrong with it, so there's nothing perfect. Anyway, we can do all this. What we see here, Model 3, this is our unrestricted model. If we were to compare Model 3 with tau equivalent, we would reject the tau equivalent model. That's what that's saying. The unrestricted model fits significantly better than tau equivalent. Furthermore, if we were to actually compare tau equivalent with parallel items, we would come to the same conclusion. Parallel items fit significantly worse than tau equivalent does. So what this is telling us is that each item matters, right? It not only does it matters with the loadings, it matters with the unique variances. So putting that all together, here are the factor score distribution again with the sum scores. Now again, I'm not wild. This is really not that different. It's 0.997 is the correlation between factor scores and sum scores. It's more what I'm building toward. Actually, this correlation is actually too high because we'll get to that in just a little bit. But again, you'll see the same phenomenon, right? We have overlap in some of the scores themselves. And why that overlap happens can be traced to what I talked about, the concept of item information before. Item information was at play in the tau equivalent items when say which item is more informative. When all the loadings are equal, we just have to pick the one with the least variance. But now the loadings are unequal, so it's not just the least error variance that we're after. We have to figure out some ratio, and that ratio is loading squared to unique variance. That's information. I had Levon calculate that for us. So item 5 had the most information. Item 3 had the least information. Right. So what you would expect in this is that a person who goes from answering 1 with everything to answering a 2 on item 5 and 1 on the others should have a bigger jump in the factor score than someone who has answered a 2 to the middle one. And that's what we see. Our factor score goes from negative 0.71 down to negative 0.29. Right. So a difference of 0.42. And that is compared to a difference of 0.31, right? So the item that matters, items matter the most by information. Those of you who might go on and take item response theory, or those of you who have taken it this year or taken it in the past, the same thing is true, right? Which items provide you the biggest boost in the factor, or the theta? It's the items that have the most information. Now, how we quantify information is significantly different in the IRT analysis, because information differs as a function of your trait itself. Right? Information is not loading squared over unique variance. It's something that involves the actual factor score itself. So it's a lot more complicated. So again, you see all the differences. Now, we're in places where the differences are just very small, and it doesn't seem to make a difference. But where it does matter if we add the error back into things. And so this is what I wanted to talk about. This is my slide from last week. I changed it. I wanted something that reminded us of bright. Jennifer looked like she needs some sunglasses. She looked up and she was like, whoa. I showed this to Lisa. She's like, that's bright. So where you see green there, that's like, it's cool. No errors present. Where you see red there, that's like bad. Now, don't be like, oh, this is comparing sum score and factor score. Don't go and count up. I've got 3 greens on one and 3 on the other. This is certainly not a parallel items model for this count. Some sources of error are worse than others in this. And let's just kind of go through it. When you have a sum score, and you use the sum score in analysis, you've got measurement error that comes back into play right here. Oh, hey, that one, my red marker doesn't quite work. I bet I can change that though. Huh? Anyway, Pointer options. Pen, ink color. Look at that. We're going to go with purple. Yeah. Right there. We have people are like, what? So we have measurement errors back. Well, if you're like, okay, I'm going to get using the factor score. If you're like, I'm going to use the factor score, measurement error is still there, right? You still have a variance around it. So using it doesn't get you away from it. What using the factor score, or what using the sum score does, it helps you out with sampling error. Right, so you don't actually have sampling error. There's no parameter estimates that you're really doing. You just have to count. You don't have to worry about the factor distribution shrinking scores toward the middle, smushing them. Excuse me, I call it squished. Squished. My wife uses the term smushed for another thing in statistics, so this is what I call squished. Prior distribution. And then there's some source of error I didn't even tell you about before. By the way, our ML estimators are biased. We know about this in multi-level, but we never talk about it in CFA. That there's another source of error for it, but we don't have to worry about it either. But if you're using the factor score, these are present. You have to have a large enough sample to believe that your lambdas and your unique variances have very little variability, right? If you're using a sample of 100 people, that sampling error is going to be large, right? If you try a sample of 100 people, you get your estimates. You see the standard error of the estimate, you'll have a wider standard error than if you had a sample of 1,000 people. And what that really is telling you is if you think about sampling again, do that 100-person study over and over again with the same population, right? Draw 100 people at random. What you'll see is your factor loadings, your unique variances will bounce around. Every time they bounce around, remember the factor loadings, the unique variances is what gives you the factor score. So if those bounce around, your factor score is bouncing around, right? So there's error. That's not good. So you need a huge sample to get the factor score right. So those of you in educational testing, like when we talk about the GRE score being a factor score, item response theory is what we use usually to build our factor scores in educational testing. We have thousands of people involved, so that we try to get rid of sampling error for that reason. Right? Sampling error is gone. We have thousands of people. Each of our parameters has a standard error that's so tiny that even if we sampled from it, it wouldn't change the result much. Anyway. We also have the prior distribution bias. That factor's there. We have an estimator bias in the factor score. But where we get better is that in the factor score, we actually are doing better because we can assess the dimensionality. We can assess whether or not we have the same constraints when compared to the sum score, and whether or not our prediction mechanism, our linear prediction function. What do I mean by that? We have a linear regression model that says the item response is equal to some linear function of factor. What if it's nonlinear? What if it's like a quadratic or something like that? All these are green because model fit. When we switch over to a factor score, we get model fit information. Right? I guess under the context of what I just showed you, we could always do that with the sum score too. We don't usually. We do. The last two things are things that disturb me even to this day. What about the data? Yeah, data, if they're not truly normal or not truly continuous, we have error. To me, this right here, this one's going to be the biggest source of error right there. That one. I think that one's so much more error. Like you see that correlation between factor score and sum score here. We were at 0.99. If you do that with switching the model up to where a more appropriate distribution might be, your correlation is like 0.8, somewhere around there. I actually did it. I didn't show you it. Didn't want to open that door yet. And then a newer one is what's the distribution of the factor itself. I asked this one because what if you really don't have a scale? What if you have just two types of people? If you plug it into a CFA analysis, it will give you a scale for the factor, right? But you look at this plot of the data from before. I know I'm late on the break. Pardon me, I will get done in just a second. But like there's two types of people, right? There are people who absolutely do not gamble, and there are people who do, right? Our factor score will not come out that way. It'll have a distribution to it. Try to be continuous distribution to it. It'll mirror this quite a bit, but you'll have a continuum to it. So if that's not right, then you're stuck as well. So this is trying to outline what are the sources of error that I've kind of tried to note are, and how they apply to both of these. When we come back from break, we're going to talk about how to fix some of these and get us a little bit closer to where we want to be. So take a 10-minute break. I will talk to you at the end of it. Thank you. Anybody have a